So our next topic is numerical methods, introduction to numerical methods. So in physics we come across so many different types of integrations, differentiations and so many calculations, equations. Okay, some of the equations, let's say integrations and differentiations, some are exactly solvable and some are not solvable. So solving a linear equation or non-linear equation, some equations may have exact solutions, some equations may not have exact solutions. So in that case, we use these numerical methods where exact solutions does not exist or exact solutions are difficult to solve. So basic fundamental rule here is whatever function we consider should be expandable in a Taylor series. Okay, so whatever function you have given should be able to expand it as a Taylor series. So whatever function you take, to be able to expand the function as a Taylor series, you must know the differentials of the function. First derivative, second derivative or nth derivative of the function must be known to you. Then only you will be able to expand it in a series. Right? So you should know the value of slope of the curve when first derivative, second derivative, third derivative at a particular point. So if you know that, you will be able to expand the function in that. Let's say, you are given some random graph like that. Some function is existing like that. Okay. So what all you know is, let's say, this is the graph of x is equal to constant. Sorry, y is equal to constant. This is the graph of y is equal to x. Right? This is the graph of y equal to x. And next, let's say this is the graph of y is equal to x square. Another graph x cube. It may look like this, x cube. So in your function, what are the combinations that exist? Either a constant or a function of x or a function of x square or x cube. Once you get a combination of these, you may be able to regenerate that graph. Right? With what information? At a particular point, if you know the slope of the graph at a particular point. At a particular point, if I know whether it is functioning as x square or x cube or x or constant, I should be able to predict the future of the graph. Right? So the basic information needed is slope of the curve at a particular point. First derivative, second derivative, fifth derivative, nth derivative of the function at a particular point. If that information is known, you will be able to predict its future. Which way will it move? Either it is continuously rising, or if you take a combination of these two, at some point it may rise, at some points it may drop, because one is positive, one is negative. And if you take another term also, x power 4, If you take combination of these two, you may get some variations in the final outcome. So how to arrive at this Taylor series expansion is a matter of discussion that we will see in the next session. But ultimate aim is we should be able to expand any given function as a Taylor series expansion. So then what happens? Whatever function, even e power x can be expanded as a Taylor series. So all you need to know is only derivatives or a type of the function at particular point. Then you can apply all your mathematical operations over this. Even if you don't know the derivative of e power x or something else, and if you just know the derivative of x, x square, x cube and all, you'll be able to get the result. So that is the fundamental idea in numerical methods. So you'll be able to dissolve the function, given function, into a Taylor series and then apply whatever further operations you need. Okay, so even if you expand this as a Taylor series, at certain level of accuracy you don't need to consider higher order terms, right? So if your exact result is 1.2357, let's say, if you add some 3-4 terms, if you get the result 1.2356 up to 3 decimal points, your result is accurate. I mean, if you restrict to 3 decimal points, happy, result is accurate. I mean, if you need further accuracy, you may have to increase your number of terms in the series, right? So the next question comes while using numerical methods is error estimation. I mean, how far is it from the original solution? That should be estimated. Okay, so errors are basically of two types. One is truncation error. Truncation error arises when you neglect some of the higher order terms in the series. When higher order terms are neglected in the series. That is a truncation error. Second one is round off error. So when you are rounding off, the numbers, if the next number is above 5, greater than or is equal to 5, add +1. If the next number is less than 5, add nothing, add 0. So in this series, let's say if you are rounding off at 3 decimal points, what happens? That becomes 1.236. Round off. And if you truncate it, it becomes 1.235. truncate the result to 3 decimals, it is 1.235. If you round off the result to 3 decimals, it is 1.236. Okay, so these are the two types of errors that we come across in numerical calculations. And coming to error estimation, so how much is that error is a matter of discussion again. So error estimations are 3 types. One is absolute error. So I'm talking about error estimations. How much you are giving a numerical value to the error. How much error is that? The first one is absolute error. So it is obtained by EA is equal to x exact minus x calculated with an absolute modulus. Exact value minus calculated value, absolute modulus. So absolute error is a positive number. But you cannot get a comparative statement from that. Let's say if your aim is to measure the value of 100 and you got 98, error is 2. And if your aim is to get the value of 1 lakh and you got 99,998, there also error is 2. But which one is better? Yeah, so 99,998 is a better calculation because out of 1 lakh you got only 2. Here out of 100 you got 2. So next, this information is not sufficient when you compare 2-3 results. 2-3 results of 2-3 different measurements or 2-3 different systems. So in that case, we go for relative error. It is obtained by E absolute by x exact minus x calculated by x exact. So you'll be comparing the error with the original value. So definitely you'll get a number less than 1 because this is what? 1 minus these two are equal, you'll get 0, otherwise you'll get a number less than 1. And sometimes it may go beyond that, depending on the error. So next one is percentage error. It is E relative multiplied by 100. So it is obtained by x exact minus x calculated by x exact So these are the three types of error estimations we use in numerical methods. Absolute error, relative error, and percentage error. So basically, numerical methods begin with Taylor series expansion of any given function, and then errors arise by two methods. One is by truncation, another by rounding off. Truncation arises when you neglect higher order terms in the series. Round off arises when you round off the result. So estimation of errors are three types: absolute error, relative error, and percentage error. Absolute error is defined when you consider the exact result, compare the exact result with the obtained result. Relative error, the difference is compared with the original result. Here it is multiplied by 100 to represent the result in percentages. Okay, so that is the basic idea. So now we see these estimations. Let's say in the case of sin x, or estimation of value of pi, let's say. So pi value is exactly defined using a tan inverse pi by 4. Sorry, tan inverse 1.0. So a built-in function is there in FORTRAN for tan inverse, a tan, arc tan. So if you go for arc tan 1.0, this value is equal to pi by 4. Okay, you can compare that value with any Taylor series expansion of sin x or cos x functions. Even you can take Taylor series expansion for tan x. So this is the exact value. So how to write that? So I'll be starting with pi exact. I'm defining a variable pi exact. So program name errors. And I'm using implicit none. I'm defining a variable real number pi underscore ex, pi underscore calculated cal. And x, the variable in Taylor series. Let's say. Now I'm defining pi underscore ex. Exact value is equal to 4 times a tan 1.0. I mean, to represent the real number, you must use point. Otherwise, it will be considered as integer. Tan 1, I mean, arc tan 1 may not give you exact result. You need to give real number as input to that. So arc tan 1.0. So now you need to have Taylor series expansion for this. Taylor series for tan x. Check that. So that is pi exact value. Now I'm considering, let's say I take sin x. Let's say I want to get the value of sin pi by 2.